In our next section, we're going to look at using BGP to automatically discover the endpoints of the VPLS network. But before we get into that config, let's quickly recap what we did up to this point with the basic VPLS example, look at how the signaling is working, and then we'll see how that is going to change when we're using BGP plus LDP and then BGP plus BGP for signaling. So again, if we take a look back at the diagram, what we have is 3 PE routers, which are router 2, router 4, and router 5. And we have them configured in a full mesh of pseudowires, full mesh of layer 2 circuits. This is what we configured under the virtual forwarding instance, or the VFI. Then we had the physical interfaces, which were the service instances that were attached on the Ethernet interfaces. We then put these as part of the bridge domain. Okay, this is what was having router 2 locally bridge the traffic between those physical interfaces. We then take the VFI, add it to the bridge domain. The end result is that logically router 2 sees the pseudo wires as physically attached circuits that we're bridging traffic between. Now, one of the behaviors that's also important to understand here with VPLS is that since we're not extending spanning tree over the provider's network, there is a possibility for a layer 2 loop. And the way that it simply prevents that is based on split horizon behavior. So what we would see is that when traffic enters on the service instance, or basically the attachment circuit down to the customer, that traffic can be bridged out to other attachment circuits, so downstream towards the customer, and then it can be bridged upstream towards the other pseudo wires. The difference, though, is going to be when traffic comes in a pseudo wire, like when router 5 receives traffic in from router 2, this can only go downstream towards the access layer, towards the customer. It cannot go across another pseudo wire to another member of the VPLS. We'll see where this is going to be significant when we look at our next example after this, which is going to be a hierarchical VPLS. But someone had a question based on that, is the split horizon behavior. It's automatically on by default. So specifically from a config point of view, if we look at this on router 2, let's just look at the show run. And let's parse through this to see what the full config is going to look like. And you'll see there's really not that much that's involved with this. It's honestly less complicated than the L3 VPN variations that we had done previously, because we're not really dealing with potential problems with VPN, v4 BGP in the core. As long as we establish just the core LSP between the provider edge routers, the rest of the config is just going to be these couple commands on the PEs. So first off, we have the VFI. Okay, well, technically the VFI would be configured afterwards. So let me reorder this in this manner, which is this. Okay, so this is basically the full config. We first have the physical port. Physical port is defining the service instance. This again is saying any traffic that comes in for any VLAN, we don't care what it is coming from the customer, we're going to say it's part of this instance. The instance is then part of the bridge domain. So gig 2, service instance 1. The VFI is specifying who are the remote neighbors. The VFI is then likewise added to the bridge domain. This is what it's causing us to receive traffic in from the pseudo wire and then forward it out the physical port that's going to the customer. Okay, from a verification point of view, we first want to make sure, are we learning MAC addresses from the local circuit? So if we look at the show bridge domain, we should see on these physical interfaces that we're learning traffic about, or we're learning MAC addresses from the customer edge routers. Okay, then we should also see that we're learning MAC addresses on the pseudo wires. If we look at the show MPLS L2 transport virtual circuits, we see the virtual forwarding instance is up. Go into router 4, go into router 5. Then if we show MPLS L2 transport VC detail, this shows all the negotiation between them. Okay, one of the most important points about this is going to be the MTU. So same as I mentioned in L2TPv3 and Atom-based point-to-point circuits, if the MTU is different between the two of them, then they would fail to do negotiation. Most of the time it's going to be the same on Ethernet, that it's typically either 1500 or 9216, which is going to be jumbo MTU. But if for some reason it was configured different in the middle, then you would need to match it on both sides of the circuit. Okay, also if we look at the show MPLS LDP neighbors, we should see that we have targeted sessions that are going from us to the other endpoints of the tunnel. When we look at the show MPLS forwarding table, we see we have the layer 2 circuits. These are going out our local attachment circuits. And then we also have the transport labels that are going to the remote PEs. Okay, this is what's establishing the transport to router 4, to router 5. And then once the traffic gets to them, they're looking at their own local L2 VPN label in order to figure out, do I forward the traffic out this point-to-point link, like this one is either gig 2 or 3, and then this is the other local service instance. Now again, from a scaling point of view, one of the limitations from an operations point of view is going to be that if we want to add another site, we need to manually provision it on all of them, where L3 VPN doesn't have that problem. Simply based on the route target import and export policy, if we add another site, we don't need to touch anything on the existing PEs. This is the main thing that BGP Autodiscovery is trying to fix. That if we want to add new sites, we don't need to touch any of the other ones. The only thing we need to do is just add them to the BGP hierarchy somehow, either as full mesh iBGP or as a part of the route reflection network, and then based on BGP advertisements, we'll be able to figure out what endpoints do we want to signal towards. So the change in the config here then is not going to be part of the service instance. It's not going to be part of the bridge domain. The only thing that's changing is the virtual forwarding instance of how are we figuring out what those particular neighbors are. Okay, so let's go ahead and remove the VPLS context from all three of these. Yeah, because I don't believe that you can change it. I think we need to delete it before we can change it. Okay, delete the VPLS context, says remove references to the VFI. Okay, so we're going to have to actually, let me paste this in here. We're going to have to do a couple steps. Okay, we first need to remove the bridge domain before we can remove the VFI, is what it is. Okay, so that's on 2, 4, and 5. From the customer edge routers, we should see that they're going to lose their adjacencies. And if we ping the broadcast address, we'll see router 1 does not have transport to the other CEs anymore. Okay, so 7 and 8, these are being ridged. Or let's see, why did it not? VFI removal failed. Please remove the references to the VFI before removal. This is because, actually that's because of the hierarchy of the config. I need to do, let me just do this. No bridge domain and no L2 VPN. Four and 5. Okay, so now router 1 should not have reachability to the other endpoints anymore. Okay, so again, we're still going to have the bridge domain that is calling the service instance on the physical port. It's still going to be calling the virtual forwarding instance. The difference is that inside the VFI, we're not going to specify the neighbors manually anymore. Now, this will imply, though, that we have some sort of BGP config that's going to be exchanging the routing information. So let's say we're now going to do this based on a route reflection design. We're going to take router 6 in the middle, and this is now going to be our layer 2 VPN route reflector. Syntax-wise, it's the same as any other BGP configuration we've already done. Only difference is that we're changing the address family to L2 VPN as opposed to VPN v4, VPN v6, etc. So from router 6, let's go ahead and configure this as a template because this is going to be our route reflector. So we're going to say that we have, under BGP, let's say this is BGP 1. We're going to define a template that is for the peer sessions. And we'll say that this is L2 VPN. And we're going to specify the remote AS is 1. And the update source is loopback 0. And then we need to specify a peer policy, or a peer policy here, template peer policy. We'll say is L2VPN. The address family is going to be, well, this is under L2VPN, we're applying it. We're going to say that the we're send community extended, and they are route reflector clients. Now, I'm not 100% sure if this is a bug in this individual version that I'm using here, but one of the key differences here between L3 VPN and L2 VPN when you peer with BGP, for whatever reason, it doesn't add this command in for you, which is send community extended. The problem is these attributes are encoded as extended communities, just like an L3 VPN, VPN-v4 advertisement. So if you don't put this command, they'll establish the BGP peering, but they won't advertise any routes. And the end result is that the pseudo wires won't signal to each other because they don't know about the endpoints. But again, when you say like address family VPN-v4 or address family VPN-v6, they automatically send extended communities. Okay, so now we're going to configure the peers. Let's say under BGP1 that we have the neighbors. Neighbor 2222 is going to inherit the peer session template that we called L2VPN. Okay, same with 4 and 5. So the templates aren't required here. It's just kind of a shortcut since we have the same config going on to all of them. So we're peering with those 3. And then under address family is going to be now L2VPN. L2VPN, and the sub-address family is VPLS. Okay, EVPN is for PBB, Provider Backbone Bridging EVPN, which is basically the next generation of VPLS, but unfortunately CSR 1000V doesn't yet support this in the data plane. So it can be used as an EVPN route reflector, but it can't be used for regular peers. So we'll say address family L2VPN. If you just hit enter here, it means VPLS. But we could likewise say address family is L2VPN VPLS. And then the neighbors are 2222. It's going to inherit the peer policy, which is L2VPN. Activate the neighbor first. Okay, neighbor is activated, and then inheriting the peer policy. Okay, so same thing with router 4 and 5. So we'll say this guy is 4444 and 5555. Okay, so if we show run section BGP, this looks basically the same as it would for L3 VPN. The only difference is that the address family is L2 VPN as opposed to VPN v4 or VPN v6. Okay, from the other side, it's going to be a little bit simpler, that we're just going to peer with the route reflector. So we'll say under BGP1, the neighbor is going to be 6666. This is router 6's loopback. Remote AS is 1. The update source is loopback 0. The address family is L2 VPN. The neighbor is activated. Okay, so let's do this on router 2. Okay, if we then look at the show run section BGP, notice as I mentioned, what is missing here under the address family is send community extended. So it may be just a cosmetic bug in this particular version. I'm not 100% sure how it behaves in the other newer code, but just be aware of this, that if for some reason it doesn't automatically show up, you have to add it in, because the attributes are encoded as extended communities, just like L3 VPN. So neighbor is going to be activated, but then also send community extended. Okay, so this is going to be the same on all 3 of these guys. On 2, 4, and 5. Okay, now from router 6, who is the route reflector, we'll look at the show BGP, L2 VPN, VPLS all summary. Okay, all meaning all route distinguishers. We'll see that when we actually configure the VPLS, the VPN identifier is automatically going to be used to encode the route distinguisher. You can manually set it, but it automatically creates it if you don't configure it. And devices within the same VPLS would want to have the same route distinguisher and then have the same route target import and export policy. Same logic as you would in L3 VPN. Okay, but right now we're not actually learning any routes from them. Okay, so next we're going to tell the VFI that we don't want to manually specify the neighbors. Instead, we're going to do auto-discovery. Okay, so on router 6, the route reflector, let's do the debug for the updates to see exactly what they're advertising. Let's debug BGP L2 VPN, VPLS updates. Okay, so next at router 2, if we look at the show run pipe section VFI, VFI is not configured. So we're going to say we have a layer 2 VPN, virtual forwarding instance, the context name, and I'll call this VPLS BGP. Okay, we need to specify the VPN identifier. So we'll say whatever, 1, 2, 3, 4. And then we specify, and notice here when you look at the question mark, it forces you to put the VPN ID first to make sure that you don't forget it. Because unless the VPN identifier is set, you can't advertise any of the information or set up any of the pseudo wires. Okay, so VPN ID is set. Now we can say we want to do auto-discovery. Auto-discovery BGP. And the signaling protocol in this case is going to be LDP, which is kind of strange. I'm going to come back to this in a minute and talk about what the difference is between them. We can also here statically set the route targets. We could set the VPLS identifiers. We don't need to do this though, because auto route target is on automatically. It means that that VPN identifier 1, 2, 3, 4 that I use, that's going to be used to derive the route distinguisher and the route target values that are actually advertised into the routes. Okay, so let's say show run section VFI. And now we're going to bind this to our bridge domain. Okay, so similar to what we have here. We have the bridge domain, and the member of the bridge domain is going to be VPLS, and I call the VPLS underscore BGP. Okay, so all 4 of them are going to get the same config. And this is pretty much the idea of it, that since you're doing auto-discovery, it just becomes a basic template that you deploy on all of the PEs. As long as they're using the same VPN identifier and you're peering somehow with the route reflector infrastructure, you're automatically going to learn whatever endpoints want to participate in that same VPLS. So it makes it just a more plug-and-play config. Where router 2 was also saying this VFI. Okay, so this is what our new config looks like now. The VFI, and then the bridge domain. Okay, so same thing on all 3 of them. On 2, on 4, and on 5. Okay, if we look at this from router 6's point of view, we can see now they're starting to advertise routes. They're advertising routes that are specifying the route distinguisher. Route distinguisher in this case is 1:1234, where 1234 was the VPN identifier that I had configured. 1 is the BGP AS number. So it automatically is prepending the AS number as part of the route distinguisher. Then we can see what the endpoints of the tunnels are. 5555, 4444, and then 2222. Okay, if we look at the show BGP, L2 VPN, VPLS all, these are the actual routes. So we can see the details of what are they specifically advertising if we say 2222/96. And let's see what the syntax is. Just basically just the identifier. Now, what is significant about this is basically just the next hop value. So notice that there's no MPLS labels that are being used between them. The reason why is that the label signaling in this case is being done by LDP it's not being done by BGP. So it's kind of a strange config, because you would assume that since BGP is running the control plane and BGP already supports labeling, that they would just tack it onto it. But it's a separate config where you're still allowed to do LDP signaling for labels, but using BGP for auto-discovery, which allows you to integrate it with VPLS configs that had static LDP peers, and then you can slowly migrate it towards BGP auto-discovery. Otherwise, if they were two separate protocols, they wouldn't be compatible with each other.